Great, good morning. Today's lesson continues the theme about data, the way that images are represented, and we're calculating the size of an image in bits and bytes, kilobytes, megabytes, and gigabytes. There's some maths involved in today's lesson, but we don't actually have to do the calculations. The key phrase here is construct an expression. That means you don't actually do the multiplication. You write down what you'd put into the calculator or what you'd calculate. So it's an expression to do with the width of an image, the height of an image, the color depth. If you multiply all of those together, you get the number of bits required, and then it's just a case of dividing by a certain amount to get it into bytes or kibibytes, mebibytes, etc., etc. So all information on a computer is in binary. Binary is measured in bits. So if we want to work out how many bits we need to store stuff, if we want, 400 bits, you could do 2 to the power 400, and you get a huge amount of information that you could store. To work out the size of an image, well, it makes sense, doesn't it? If you've got the width times the height, and it's a grid, a bitmap image is a grid of images, you want to count how many pixels you've got, you do width times height. It's like a rectangle in maths. So the number of pixels going across multiplied by the number of pixels going up is the number of pixels that you've got. The color depth is the number of bits per pixel. So if you want to work out the total number of bits, all you've got to do is just multiply the width by the height by the color depth, and that gives you the total number of bits. So that's what we've got here. We also have some metadata which we're going to ignore. So there we go. This is the key thing to remember. Width times height times color depth if you're measuring in bits. The only slight complication is if you want to then go to bytes, you've got to divide by 8. If you want to get into kibibytes, remember that's a capital K and an I and then a capital B. A lowercase b means bits, a capital B means bytes. Edexcel insist on using these kibi, mebi, gibi, and tebi prefixes, and they are always powers of 2, as in 2 to the power 10 is 1024. So let's do some worked examples of these so that we can see what we're supposed to do. File size here, remember you're not calculating this, you're writing an expression, constructing an expression. You do the width, let's enable editing so we can see what's going on here. The width is 233. The height is 279. That would be 1 mark, or would it? It depends. It would be either 1 mark or 2 marks for this question. And then you've got to multiply by the color depth. This says the file size in bits, so it's dead easy. For all of them, we're just doing all of these numbers multiplied together. You do not have to calculate it. You don't have a calculator in the exam. You're not expected to do it in your head. That's the good news. Activity 2 is slightly harder because we've got to convert it to these particular units. So we start off with the same thing. I'll go for the middle one this time. 800 width by 600 height by 8 bits across. That would be 1 mark so far. Divide by 8 to get it in bytes. I'm going to use some brackets here to make it really clear what we're doing. That should be an X, not a Z. 800 times 600 times 8, that's the total number of bits. Then we want to divide by 8 to go into bytes. And we also want to divide by 1024 to go from bytes to kibibytes. And if you want to go to mebibytes, you just divide by another 1024, or you could do 1024 squared. Okay? So that should be enough for you to do all of activity 1 and all of activity 2. I'll pause you again before we get to activity 3. So let's go through this last one together. Construct an expression to calculate the file size in the required units for these images, and we're ignoring metadata. So that means all we've got to do is multiply the width by the height by the number of bits per pixels. That gets us 1 mark. That gives us the total number of bits required to represent the image. We then need to divide by 8 to go into bytes. We need to divide by 1024 to go into kibibytes, and another 1024 to go from kibibytes to mebibytes. Remember, if there's ever a question about file sizes, you should always write down kick my granny to pieces as a way to remember. You go from bits to bytes to kilo, mega, giga, tera, peta, or kibi, mebi, gibi, tebi, and pebi. If it's mebi or kibi, then it's times 1024. If it's kilo or mega, it's times 1000. The question will always say, but the way to remember it is if you're dealing with size, then you're dealing with 1024s. If you're dealing with speed, then it's kilo, mega, giga, then it's powers of 1000. So let's go through activity 3. It says an image is, this is exactly like an exam question. An image is 500 pixels high and 500 pixels wide with a color depth of 16. Construct an expression to calculate the file size in bits. So it's exactly like what we've done, just written out in words instead. So 500 pixels by 400 pixels, you don't need to calculate it, you just write down the expression by 16. That's it. Nice and easy. I'm going to skip ahead to part C. I'll let you do the rest. An image has a file size of 454 kibibytes. Its height is 800 and its width is 600. Work out the color depth. So let's do the equation. 554 kibibytes is equal to, we've got a bit of maths rearranging going on here, 800 times 600 times the color depth. But it's also been divided by something. So all of that is divided by 8. And then we're going into kibibytes, so times 1024. So we need to multiply things out to get just the color depth. So how can we do that? A bit of maths involved here. So 454 multiplied by 8 multiplied by 1024. So that's multiplying out these bits. All of that divided by 800 times 600 will give you the color depth. Oops, color depth. So we have to be able to rearrange some equations here. If I want to get rid of the division on this side, I have to multiply both sides of my equal sign by the same thing. That will cancel that. And that's why I've got that multiplied by 8 times 1024 over here. Then if I want to get rid of the 800 by 600, I have to divide this side by 800 by 600, which means I have to divide this side by 800 by 600. Notice you do not need to do the calculation. You are always just constructing an expression. I'll give you a few more minutes to work through activity 3. So for the final activity then, we're talking about the impact of changing certain properties of the image on the resolution, the storage space, and how long it takes to transmit a file. So there's different definitions of resolution. For Edexcel, GCSE Computer Science, we're talking about the number of pixels per inch. So that means if we have, like, imagine each of these are pixels, maybe that looks like an inch to me. That's 1, 2, 3, 4, 5 pixels per inch. If you have your pixels closer together, the same amount of space, I've now got, what, 8 pixels per inch. It just means how close together the pixels are. Further apart they are, the more pixelated it looks. The closer together, the higher quality it looks. If you double the width and the height of the image, it makes no impact at all on the resolution. The resolution is still going to be the number of pixels per inch. The resolution will not change. The storage space will change. It will get doubled if you double the width, and then doubled again if you double the height. So the storage space is going to get squared if you double both width and height, but it's enough to say it increases. Which makes sense, doesn't it? You know on your phone, if you take a higher quality picture with more pixels, it's going to take more space. Network transmission, well, if storage space goes up, network transmission speed goes down. So it's going to take 4 times as long to transmit it over the internet if it takes 4 times as much space because we've doubled the width and doubled the height. But the resolution stays the same. Remember, resolution means dots per inch, pixels per inch. If the number of pixels per inch has tripled, well, that is the definition of resolution. That means the DPI has tripled. We've gone, say, from 100 pixels per inch to 300 pixels per inch. It means it's going to look crisper and sharper, clearer, better quality. It's also going to be a third of the physical size when you look at it on your screen or on paper. It's going to be physically smaller, but it will take up the same amount of space on disk. It's still the same number of pixels, it's just the pixels are closer together, so storage space is the same. If storage space is the same, network transmission is the same. Nothing's changed there. It's still the same number of bits. Those bits still have to be transmitted. It takes the same amount of time. This one's interesting. The color depth has been reduced from 24 bits per pixel to 8 bits per pixel. The resolution is the same. The number of pixels per inch is identical. Storage space has been reduced by a factor of 3. 8 is 24 divided by 3, so we're only using 1 byte per pixel instead of 3 bytes per pixel, or 1 set of 8 bits per pixel instead of 3 sets of 8 bits per pixel. So we're reducing the storage space by a factor of a third. If we're reducing the storage space required per the image, we're increasing the network transmission speed, decreasing the network transmission time. So if it's going faster, it takes less time. Agreed? Explain one reason why it's acceptable to change the properties of an image. Well, sometimes if you've got a really high quality image and you want to put it on the internet, it's going to take too long to download if it's really high quality, so you'll reduce the height and the width so that it takes up less space so it downloads faster. Or in iMedia, we talk a lot about exporting to 300 DPI, which means we need more pixels. So the storage space goes up. Download time also increases. The important thing from today's lesson is that you know this magic formula, which is the file size is the width times the height times the color depth in pixels divided by whatever you need to divide by to get into the required unit. So that's always dividing by 8 to go into bytes from bits, and then usually dividing by 1024 to get to kibibytes, and then by another 1024 if you need to go to mebibytes, and another 1024 if you need to get to gigabytes. And remember, you never have to do that calculation. The key phrase to remember is construct an expression. That means write down what you would put into a calculator, show you're working, but don't actually calculate. Okay, I'm not going to put an extension on for today. So when you've done this, this gets saved in your data topic, topic 2, and it gets uploaded to half term 9. Half term 9 data 3 is where you upload it to, please. Make sure it's saved in your topic 2 data folder at school. Upload it to half term 9 data 3.